Okay, we're picking up where we left off in the previous video. We're going through Chapter 2, Section 5 on continuity. We've already gone through the majority of this section, but the last topic the textbook discusses is the intermediate value theorem. This theorem is directly related to continuity, which is why it's included in this section. Okay, so an important property of continuous functions is expressed by the following theorem, whose proof is found in more advanced books on calculus. So, okay, this theorem and other theorems like this that we're going to learn in this course, some people would consider kind of mathy. So, like, as I've mentioned before, this is not a channel designed for mathematicians. This is an engineering channel. The math playlists are really designed for people who apply math in their respective fields. So like for a math major, you would want to go through all of the theorems and proofs in a calculus textbook like this in detail, right? So like for a math major, you would want to go through all of the theorems and proofs in a calculus textbook in detail, right? So not just the meaning of the theorems, but even the proofs. But these math playlists aren't for math majors, which is why we skip over most of the proofs and other unnecessary details. Okay, but still, theorems like the intermediate value theorem, the extreme value theorem, etc., are useful to go through and understand even for non-math majors. Theorems like this will come up later in this course, but they also come up in subjects such as numerical methods, for example, which is a really important subject for non-math majors because as non-math majors, we're big on getting numerical solutions to problems. There's arguably no subject more fundamental to what it means to be an engineer than numerical methods. So like, for example, as an engineer or chemist, scientist, etc., you might have some system you're trying to model. You model the system, you apply some differential equations, you add as many variables to the system as you deem necessary. But then when it comes time to solve all of the equations simultaneously, there might be no way to solve everything for an exact solution because it's just too complicated. But numerically, you can make some algorithm that can give you an approximate solution. But like I know when I was younger, I would hear the term approximate solution and think, well, no, I don't want an approximate solution, right? What use is an approximate solution? But I was misunderstanding the idea that, remember, you can let your program run for, it might not even take 30 minutes. It could take 5 minutes. But like the meaning of an approximate solution is that, so even if you got your answers to your variables precise to within 10 decimal places, 20 decimal places, that's still technically not considered exact. An exact solution mathematically is correct to like an infinite number of decimal places. It's exact. Well, but solving your system for like a real life system to 10 decimal places of precision, in the vast majority of cases, that's even way more precise than what you need, right? Like a temperature or a speed or a weight or whatnot, or an amount, you only need 1, 2, or 3 decimal places. You take that all day. So like numerical methods are huge for non-math majors. And so again, theorems like the intermediate value theorem come up in numerical methods. So, okay, what's the intermediate value theorem? It says that suppose that the function f is continuous on the closed interval from a to b, and let capital N be any number between f of a and f of b, where f of a is not equal to f of b. If those constraints are met, then the theorem says that there exists a number c in the open interval from a to b such that f of c is equal to capital N. So as we break down what this is saying, note how this might seem trivial or kind of like an obvious statement. But just remember, as we've talked about before, to construct a subject in math, science, etc., you have to be very precise when it comes to definitions, theorems, statements, etc., right? So, okay, let's go through what the theorem says again. So it says, suppose that you have a function. So first note that it's specifying that we're dealing with a function. So a relation that passes the vertical line test. Now, something else to note, anytime we're looking at a theorem or a definition that says we're considering some function, remember that this could be an interval of an equation or relation that on the whole is not a function, but some interval of that equation or relation is a function. Like, for example, this here on the whole isn't a function, right? It doesn't pass the vertical line test. But if you specify some interval of this relation, some interval from A to B, well, this interval is a function, right? This interval passes the vertical line test. So even though this entire relation is not applicable to this theorem, this interval of this relation would be. You see, and it's the same idea with something like a relation such as a circle, which doesn't pass the vertical line test, but if you solve the equation of a circle, the x minus h squared plus y minus k squared is equal to r squared, explicitly for y, you get something like y is equal to an expression with a plus or minus in it. Because for any given input x, you're going to have two outputs. But you can just replace the plus or minus with just a plus or just a minus, in which case you're focusing strictly on the upper half circle or the lower half circle, and alone the upper half circle or the lower half circle is a function. So by itself, you can look at the equation of the circle with just a plus or a minus here and apply that as a function to this theorem or whatever the theorem or statement is that specifies that we're considering a function. Okay, so suppose that we have a function that's continuous on the closed interval from A to B. So we have a function on some interval that's continuous. And same idea with continuous. It's not that, and the entire function has to be continuous. It's just that whatever interval you're considering has to be continuous. So like a rational function, right? Most rational functions, you're going to have vertical asymptotes at one or more locations. So the rational function isn't continuous everywhere. But on some interval from A to B, depending on the interval, then you do have a continuous function, which would be applicable to the theorem. Okay, so the function is continuous on the closed interval from A to B. Let's note that this input interval is closed. All right, now let capital N be any number between f of A and f of B, where f of A is not equal to f of B. So, okay, what they're saying is that we've got, so let's say A is, let's say A is here and B is here. So you've got f of A and f of B. Notice how they're not specifying that f of B needs to be greater than f of A or vice versa, only that they're not equal. So this could be f of A. This could be f of B. But the function is definitely defined at f of A and f of B because we're continuous on the closed interval from A to B. And then capital N is any number, any output on the y-axis that's between f of A and f of B. So any number in this range here, not including the endpoints, this open interval here, that's what capital N is, any number. And we know that it can't be equal to f of A or f of B because it says between. So N is some number in this interval. Okay, so that's the constraints of the theorem. If those constraints are in place, then the intermediate value theorem says that there must exist a number C in the open interval from A to B. So this number C is an input somewhere between A and B. such that the function evaluated at C is equal to capital N. Okay, so what the theorem is saying is that with the constraints shown here, and because the function is continuous from A to B, then if we think about the graph of the function, it is going to have to, at some point between A and B, pass through the output N, 100%. From the pen on the page perspective, it's the theorem is saying that. So if we're going to draw this function from A to B and we start at A, then there's no way for us to get to B without passing through this horizontal line at y is equal to N. There's no way for us to get from A to B without passing at least once through this line. And this makes sense because from the pen on the page perspective, if we're going to start here, we put our pen down, and we're never going to pick our pen up, then how could we possibly get to f of b without passing through this line here? Even if it was the function was a relation, there's still no way to not pass through the horizontal line at n. Okay, now it notes here how the function could pass through the output n more than once. So here it only passes through n once, but here it passes through n 3 times, right? And then at the same time, you can think about how it's not like the function can't go above or below f of a or f of b. I mean, you could have something like, right? Or it might not ever go above f of a or f of b. Like that. So the theorem just says that the function is going to pass through all output values between f of a and f of b at least once. That's all it says, right? That's exactly what happened here. Every single possible output value, because like capital N is a general variable. Capital N is any value between f of a and f of b. So that's what they're saying. You can pick any capital N you want. So what that's saying is that the function is going to with these constraints in place, the function is going to have to pass through every possible output value between f of a and f of b, going from f of a to f of b. And that's what we see here, right? Every single possible output value the function passes through at least once. Okay, and then also keep in mind that there was no constraint about f of a being less than f of b and whatnot. So here the f of a is less than f of b. Here f of a is greater than f of b. So the function is decreasing, but it's all the same. Okay, so now let's go through the theorem again and analyze the constraints. So the interval is a closed interval from A to B. Why does this interval need to be closed? Well, if the interval isn't closed, then there's ambiguity, right? Because for this theorem to really make sense, you need to have a definitive starting point and ending point. You need to say, look, okay, we're starting here at this point, f of a, and then we're going to go to f of b. If it's an open interval from A to B, well, then there's just confusion there. What exactly is capital N? You could hypothetically start anywhere, just really, really close to x is equal to a. All right, now the function is continuous over the interval. That's the whole point of the theorem. And we're dealing with a function, not a relation. Now, we can think about how we looked at, it seems like it would be the case that this theorem would apply to a relation as well, a continuous relation. Something like this, the theorem is satisfied. But just trying to prove this for a general relation is a little bit ambiguous, because you could have a relation like this. So now there's multiple paths to get from f of a to f of b. So, for whatever path you choose, if that path is continuous, then the theorem should apply. But at the moment here, they're just talking about functions. Okay, now f of a not being allowed to be equal to f of b is necessary, because otherwise the theorem can break down. So if we have a case where, so here's f of a and here's f of b, Now, here, you can't make, if you're allowing for this case, then you can't make the general statement that capital N is some number between f of A and f of B, because f of A is equal to f of B, right? But that's not a big deal. You could adjust the way the theorem is stated to allow, like in this case, you would say, okay, f of A is equal to f of B, so capital N must be equal to f of A and f of B. So the number C then would be just some value between A and B where f of C is equal to capital N. Okay? So great. We've got some continuous function. Let's see. Here's a continuous function. Well, now we just violated the theorem. The theorem doesn't work there. There is no f of C where C is some input between A and B where f of C is equal to capital N. So that the theorem is only bulletproof if it's specified that f of A can't be equal to f of B. And then at the same time, capital N is some number between f of A and f of B, which also makes it necessary that the input point for which the function maps to capital N is a number on the open interval from A to B. So not including A or B, because otherwise f of A or f of B could be equal to capital N, right? Okay, so the intermediate value theorem states that a continuous function takes on every intermediate value between the function values f of A and f of B. This is illustrated by figure 8 below. Note that the value capital N can be taken on once or more than once. Okay, if we think of a continuous function as a function whose graph has no hole or break, then it is easy to believe that the intermediate value theorem is true. In geometric terms, it says that if any horizontal line y is equal to capital N is given between y is equal to f of A and y is equal to f of B, as in figure 9, then the graph of f can't jump over the line. It must intersect y is equal to capital N somewhere. It is important that the function f in Theorem 10 be continuous. The intermediate value theorem is not true in general for discontinuous functions. Yeah, exactly. So if a function is continuous on some interval, then it can't jump over. There's no way it can jump. There's no hole. You draw the function without picking up your pen off the page. So there's no way to get from the starting output point to the ending output point over that interval without passing through every single value between the starting output and the ending output. But like it says, this is only the case if the function is continuous on that interval. Okay, one use of the intermediate value theorem is in locating roots of equations, as in the following example. So show that there is a root of the equation, this equation here, between 1 and 2. Yeah, so here's an example of something you do in numerical methods. If you wanted to find the roots of this equation, you might be thinking a couple of things. First of all, you might be thinking, aren't we able to find roots of equations like this exactly using factoring techniques from algebra? Right? This is just a polynomial equation. We can use the advanced factoring techniques that we learned about polynomials, right? The remainder theorem, the factor theorem, the fundamental theorem of algebra. So yes, that's true, but they're just giving an example here, a simple example here. Remember, all of the functions we're familiar with from algebra and trigonometry are continuous everywhere in their domains. So you could have, in general, for more typical scenarios, a much more complicated function or expression on the left side of the equation here that you aren't able to solve, exactly analytically. Now, you might also be thinking, well, what if we're trying to solve an equation with an individual expression of x like this, but on both sides of the equation, right? Yeah, this one's equal to 0, but a lot of equations aren't equal to 0 like this. Well, no, you would just rearrange that entire equation to have a 0 on one side, right? You can put any equation into a form like this where you just have an expression of x on one side and 0 on the other side. Okay, but now here we aren't actually going to find the roots of the equation, because the intermediate value theorem isn't a numerical method to be used for finding roots like this. The intermediate value theorem is just going to tell us whether or not there is a root, in this case between 1 and 2. So is there a solution to this equation somewhere between the input values of x is equal to 1 and x is equal to 2? Well, okay, what they do is they just plug x is equal to 1 and x is equal to 2 into the function and get, so f of 1 is minus 1 and f of 2 is 12. And they indicate that minus 1 is less than 0 and 12 is greater than 0. Okay, so now with that, if you apply the intermediate value theorem and let capital N be equal to 0, and this works because this is a number between f of 1 and f of 2, and we consider the closed interval between 1 and 2, well, then because this expression here we know is continuous on that interval, it's a polynomial, it's continuous everywhere, and so definitely on that interval, then the theorem says that there is some number c between 1 and 2 such that f of c is equal to 0, which would mean that would be a root, right? That would be a solution to this. Now, next, they illustrate how you can continue to make this input interval smaller and smaller to hone in on what this root is. So instead of going from 1 to 2, they go from 1.2 to 1.3, and you get a negative number and a positive number. So there is a value c between 1.2 to 1.3 to where f of that c is equal to 0. And they go even further from 1.22 to 1.23. So there's some value between 1.22 and 1.23 to where when you plug that value into this function, to this equation, it's going to solve the equation. It's going to be a root. Now, notice, though, that it could perhaps have been the case that there was more than one root between 1 and 2, because we saw how it could be the case that the function passes through that n value more than once. So the fact that the theorem was satisfied for the open interval or the closed interval between 1 and 2, and they honed in on one potential solution here. Well, maybe there was another one. Maybe there's a solution at 1.75 or something, right? So just keep that in mind. Now it says we can use a graphing calculator or computer to illustrate the use of the intermediate value theorem in the previous example. Figure 10 below shows the graph of f in the viewing rectangle minus 1 to 3 by minus 3 to 3. Yeah, minus 1 to 3 and then minus 3 to 3. And you can see that the graph crosses the x-axis between 1 and 2. Between 1 and 2. Figure 11 shows the result of zooming into the viewing rectangle. So here you're going from 1.2 to 1.3, and then minus 0.2 to 0.2. And yeah, so you can see the root, right? Because this function is continuous, as long as what you're doing is you're saying that, so here's f of 1, and then f of 2 is, we can't see f of 2, but since f of 2 was 12, f of 1 was minus 1, but since 12 is positive, minus 1 is negative, we know that at least once that this function must cross through the horizontal line at 0. Now they zoom in some more, and you've got, what was it, f of 1.2, and then f of, you can choose any number here. You're going to get a negative value here. You're going to get a positive value here. So you know the function must cross through the output of 0 between within this interval. So in fact, the intermediate value theorem plays a role in the very way these graphing devices work. A computer calculates a finite number of points on the graph and turns on the pixels that contain these calculated points. It assumes that the function is continuous and takes on all the intermediate values between two consecutive points. The computer therefore connects the dots by turning on the intermediate pixels. Yeah, so what they're saying here is that with a continuous function, the computer is going to turn on as many pixels as are available. If some output is, for a continuous function, any output that's between two outputs, it's going to turn that pixel on.